We are now going to look at a special case of waves propagating in a lossy material, and that is when the material is a very good conductor. Here we have the form of our transverse electromagnetic wave in a lossy material. So in our propagation constant, let's factor out a sigma from this second term in parentheses here. Looking back at Ampere's circuital law, and writing the conduction current as sigma times the electric field intensity and replacing the electric flux density field with epsilon times the electric field intensity, we have this form for Ampere's circuital law, and if we write it in terms of phasors, it will look like this. This first term is the conduction current density, this second term is the displacement current density. So in a good conductor, this first term will be a lot larger than the second term. So looking at this term right here, this omega epsilon over sigma, we see in a good conductor, this term will be much, much less than 1. And so in a good conductor, the propagation constant reduces to the square root of j omega mu sigma. So let's rewrite gamma like this. We can write j as cosine of pi over 2 plus j sine of pi over 2 because the cosine of pi over 2 is 0 and the sine of pi over 2 is 1. So j can be rewritten as e to the j pi over 2 using Euler's identity. So the square root of j is equivalent to e to the j pi over 4. So for the square root of j, we can make that substitution. We will rewrite e to the j pi over 4 using Euler's identity. Cosine and sine of pi over 4 are 1 over the square root of 2. So we get this form for our propagation constant. And so in propagation in a good conductor, alpha is equal to beta. Taking the ratio of omega over beta, we get the velocity for our wave propagating in a good conductor. Going to our intrinsic impedance, let's divide the numerator and the denominator by sigma. And in the denominator here, in a good conductor, this second term is going to be small, so we can ignore it. So we can write our intrinsic impedance in this form. With this electric field intensity for our wave propagating in a good conductor, this is the resulting magnetic field intensity. And we see that there is a 45-degree phase shift between the electric and magnetic fields. As our electromagnetic wave is propagating, it is being attenuated, and that attenuation is given by these exponential terms in our electric and magnetic field intensities. A useful parameter for propagation in a good conductor is the skin depth. Skin depth is the distance at which the wave has attenuated by a factor of e to the minus 1. So that's when this e to the minus alpha z term is equal to e to the minus 1. The symbol we use for skin depth is delta, so we replace z with delta and set e to the minus alpha delta equal e to the minus 1. The skin depth is 1 over the attenuation constant, so we see that the skin depth is going to vary with frequency. This table shows how the skin depth varies in different materials and at 3 different frequencies. So we see as the frequency goes up, the skin depth gets shorter and shorter. And notice that iron has a much shorter skin depth than the other materials because iron is magnetic and has a large relative permeability relative to the other metals shown. For seawater, we see that at 1 megahertz, the skin depth is only 1/4 of a meter, and at 60 hertz, it's 32 meters. So radio waves cannot travel very far in seawater, and it is why it's difficult to communicate with submarines. Another consequence of skin depth is that if you're trying to send a signal down a wire, the signal will not penetrate much more than a skin depth into the wire. If the diameter of the wire is much greater than the skin depth, then over the majority of the area here there will be no signal propagating. This is a consequence of Faraday's law, and from our mental model of Faraday's law we can understand what's happening. Here we have a wire, and here is a cross-section looking through the wire. Here I'm showing a current flowing in the wire, so looking through the cross-section we see the current is flowing up out of the page. The magnetic field intensity lines from this current coming out of the page will be these counterclockwise circles, and over here that means on the right hand side the magnetic field intensity lines will be going into the page, and on the left hand side out of the page. Let's look at what happens if you try to now increase this current. If the current starts to increase, we know the magnetic field intensity will start to increase. This changing magnetic field intensity will generate induced currents, and we know from Lenz's law these induced currents will be in a direction to produce a magnetic field opposing the increase in the magnetic field from the increase in the current down the wire. The increasing magnetic field into the page on the right-hand side of the wire will induce a counterclockwise current that will produce a magnetic field out of the page. This induced current will cancel currents on the interior of the wire and increase the currents near the exterior of the wire. Similarly, on the left-hand side, the increasing magnetic field out of the page will induce a clockwise current. The clockwise current produces a magnetic field into the page. The induced currents will cancel with the currents on the interior of the wire and increase the currents near the exterior of the wire. The currents flowing in the wire are pushed towards the edges of the wire. The higher the frequency, the greater this effect will be. So as the frequency goes up, the signal is being carried by a smaller and smaller portion of the wire. Here we have a cross-section of a wire of radius A. Shown is the situation where the AC frequency of the signal being propagated down the wire is such that the skin depth is much less than the radius of the wire. In the case of DC, the current is flowing throughout the cross-section of the wire. So for a wire of length L, we know that the resistance in DC would be the resistivity times the length of the wire over the cross-sectional area, which is pi a squared. To approximate the AC resistance, let's take this skin depth cross-sectional area here. So I've redrawn this ring here, so its thickness is delta, and the length will be the circumference of this circle, 2 pi a. So in AC, the signal is just flowing through this cross-sectional area. So in AC, the resistance of a length L of this wire would be the resistivity times L over this cross-sectional area, which is 2 pi a times delta. So the AC resistance is going to be quite a bit larger than the DC resistance. Earlier, we found this relationship for the skin depth. The skin depth decreases as the frequency goes up. So with making this substitution, we see that the AC resistance of a wire will increase with the square root of the frequency of the AC signal. If you're working at DC, you can always lower the resistance of your wire and the loss in your wire by increasing the cross-sectional area. If you're working at AC, once you get more than a few skin depths, say about 4 skin depths in diameter, further increase of the wire diameter is not going to reduce your resistance because the power is all flowing in the periphery of the wire. Remember when we talked about the war of the currents and how AC transmission won over DC transmission in the late 1800s because you could use transformers to step up the voltage and step down the current and reduce the I squared R losses. But if you could do the same thing with DC, then you could get a transmission line with lower losses because you could always make the wire diameter larger. Today we can use power switching transistors to do that, to step up the voltage and step down the current for DC. And so today the most efficient power transmission systems would be DC and not AC. There are in fact some DC power transmission systems now, and I'm going to put up a copy of an article in case you're interested entitled DC Supergrid.